All right. So, welcome, y'all. Last class, so we started talking about energy and work. So we defined work as basically how much energy something gains or loses. Work is how much energy something gains or loses. And what is a way that we can gain or lose this? The equation was work is the integral of F dot dr, which basically says you apply some force over some distance, and that increases or decreases the energy. This dot is a dot product. A dot product is a way of multiplying vectors, where you find the component of the vectors that are parallel to each other, multiplies them, and makes a scalar. Energy is a scalar. All energy is a scalar. And so we kind of talked about that, did some problems with it, thought it through. We got to see free body diagrams again. It was a great time. So much fun. So to give us kind of a quick recap on that, we'll solve a problem on it, then keep moving and grooving. So the question is, how much work does the force F of x equals -2 divided by x newtons do on a particle as it moves from x equals 2 meters to x equals 5 meters? So what's given here? We have, some function for force, -2 over x. We know my x initial is 2 meters. We know our x final is 5 meters. What are we solving for? Work. Okay, so just basics. Just writing down the information. Again, I'm being a bit more kind of thorough. In general, if you see the word work and force, your mind should immediately go to this equation. And you look at this and you say, what? Like, there's no x's there. So when it comes to integrals, this integral is going to become this, fx dx. So a dot product can be written as the magnitude of the two vectors times the angle between them. If they're both in the x direction, the angle is 0. So it ends up becoming this. This is a good thing to kind of look at, think about, see if you can kind of piece through what happened here. So magnitude of f times magnitude of dr. Whatever. Yeah, if I think I write more, it would be more confusing. But basically, that's what it kind of comes down to. And so then at this point, it's just doing the integral. So work is going to equal the integral from 2 to 5 of my function, -2 over x dx. So the force, F is a function, so we plug that in. R is the direction of motion. It's an x, so we just replace R with x. And the dot product goes away because they're parallel, x and x, they're the same direction. Yeah, see if y'all can do this integral. Try it out. I'll give you a few moments. It's a fairly simple integral. I'm not going to be giving you all any gross integrals. There's no trig sub going to be happening in here. I don't know if you got to that point in Calc 2. No trig sub, no u sub. In general, it's just kind of power rule stuff. Okay, so this one was a little, so we can pull that -2 out to the front. And it's natural log of x. How fun. From 2 to 5. So you get -2 ln of 5 minus ln of 2. And at that point, whatever you plug it in, you get a number. Woo. Not too much to say there, honestly. That's a number, it's not a huge deal. The final answer will be in joules. It is good to remember what the unit is. So we'll put a little J here for joules. That would get chucked there, but Yeah, I mean, the last step is just pointing back there. It's not really too worthwhile. So fairly straightforward. Kind of shows us how we use this whole integral situation. If you only have to do this integral if I give you a function. I have to give you a function for you to kind of have to do this integral. Otherwise, basically, any force I give you will be constant. It's a good kind of rule to have somewhere in your head. The only way, I'm not going to make you all come up with the function for force. That would be messy and very involved. And I'm not even sure what that problem would look like. So, if you all see a function, just know that you're going to integrate it. And again, you all aren't in Calc 3, so I'm not going to make you do double or triple integrals, because you haven't learned them yet. So when you're integrating, you're just going to integrate along one dimension. Makes your all's life easier. All right. Cool. Any questions here? Because this kind of ends our little section on work. It's it's going to keep popping up, but this is kind of the main chunk. This kind of finishes up what we talked about Monday. Okay. So the next thing, I said it ends it. One last thing I want to point out here. So remember, work is an integral. So if there was a graph, an integral is the area under the curve. So for example, in this problem, if we wanted to find the work done and we had a graph of force to x, you would just find the area under the curve. That's it. Now I'm not going to really say too much more than that. That's it. So, area under the curve, you do the rectangle, 5 times 4, and then you have a triangle, 1/2 base times height, whatever. If you don't see one like in the problem set, you don't need to worry. And hey, look, here's the problem set. Let's check. Boop, 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 boop. Did I give you any area under the curve? Nope. So, I'm not too worried about, I'm not going to make you all do that. But it's good to point out. It's good to remember what an integral does graphically. A derivative gives you the slope, an integral gives you the area. All right, first clicker question. I push a heavy box across a rough floor in a straight line. So there's my straight line. Woo! Someone else takes a crazy windy path, as shown below. If friction is at work, friction is at work. If friction is existing, who had to do more work? So I actually don't want to use this word work here because it's kind of using the everyday definition and not the science definition. If friction exists, who had to do more work? I mean, technically, I guess it is at work. So that's me as a straight line. Is that one more work? Someone else? That's the windy path. So the red arrow here, that's me. The blue windy path, that's someone else. And option C is the work is the same. All right, we'll go to 120 on this. There's no math here, just thinking through it. All right, and 5, 4, 3, 2, 1. Okay, so there's a couple ways to think this through. Let's think about it mathematically. So the definition of work equals the integral of force dot the distance, which again turns into this. I think it's easier if we look at it in magnitude. F dr times the angle between them. When it comes to friction is always opposite the direction you're moving. Which interestingly means in this problem, theta is 180 no matter which way you're going. Because no matter which way you're going, you're pushing in a direction, friction is the opposite way. Whatever way you're moving, friction is exactly opposite. It does not matter where you are, which way you're going, no matter if I'm pushing it this way. So if I'm pushing it this way, friction is the other way. If I'm at this spot and I'm pushing it this way, friction is the other way. So friction and the direction of motion are always opposite to each other. So it is always cosine of 180, which makes it negative. Why does that matter? That means the path matters. The longer the path you take, every extra step that you're pushing that thing, you are having to do more, friction is doing more work. The path matters. The path matters because no matter what you're doing, there is a friction work. Wherever you're going, friction is doing work. If you're going left, it's the same amount of work as going up. It's the same amount of work as going that way. The path matters. The path matters. So someone else is having to do more work. They are having to put more energy into it to make this happen. Okay. Boom. Now, a different scenario. One car goes flying off a cliff and hits the ground. A different car takes a nice, safe road which winds down the cliff and ends at the ground. So here we go. We got, woo, there goes the car that flew off the cliff. And then this other guy's, doing a windy path and ends up at the same spot. In which case was the work done by gravity greater? In which case was the work done by gravity greater? So basically the same question as last time, but instead of it being friction, it's gravity. We'll go to 110. All right, we'll close it out in 5, 4, 3, 2, 1. All right. So we're going to start the same way. Integral f dr cosine theta. But here's where it gets messy. In the last problem, friction always pointed opposite the direction you're moving, so the angle was always 180. In this problem, gravity is always down. So the angle is changing. At this spot, in the beginning, this car is going this way, so the angle is right here. At this spot, the angle, oh, that's the angle. This one, the angle is there. At this spot, the angle, so gravity is down, the angle is this way. So y'all can see the angle is changing constantly. At this spot, the angle is this big thing here. The angle is constantly changing, and you're just going to have to take my word for it, that the result of that, when you're going up versus going down and all of that, and if you actually did all the math for this crazy path, the path doesn't matter. That the work done by gravity is the same. If you kind of did all this crazy math, anytime you're going upwards, that kind of cancels out going downwards. Anytime you're going left, like at an angle, when it comes to gravity, all that matters is height. Up, down. Gravity doesn't care about left, right. That's something we have talked about. Gravity doesn't care about whether you're moving to the left. Gravity doesn't care if you're going at an angle. All gravity cares about is the up, down. It cares about where you start and where you end. Yeah?
So does the work done by something not matter about its change in position?
That's a great question. And so the answer to that, it depends. So on the last problem, it mattered. With friction, it matters. With gravity, it doesn't matter. And then you're like, okay, how do I, what's going on here? This is a nice summary. There's forces called conservative forces and forces called non-conservative forces. Conservative forces say the path doesn't matter. The amount of work done doesn't matter. If I take my water bottle and I make it do a weird dance but it starts here and it ends at the ground versus me just literally dropping the thing to the ground, the work done by gravity is the same. The path doesn't matter. So gravity, an elastic spring, the electrostatic force, that's physics 2 stuff. All of those are path independent. There are forces, and how do you actually know that that's the case? All those forces are always kind of in the same direction. Gravity is always downwards. Who cares which way the thing is going? Gravity is always downwards, and where you're located doesn't necessarily change. Well, even if it did, it wouldn't matter. Non-conservative forces, the path matters. And these are basically pushes or pulls. Friction, applied forces. The non-conservative forces are forces that have to do with the direction you're going. Non-conservative forces are forces that are affected by the direction you're going. Friction is affected by the direction you're going. The applied force is affected by the kind of direction you're going. Air resistance is affected by the direction you're going. Gravity doesn't care which way you're going. Gravity affects everything the same. That's the way to kind of remember that. Gravity doesn't care what you're doing. It still pulls with the same force. Friction cares about which way you're going. It's always pointed the opposite way. Okay? So we have this conservative and non-conservative. The reason they're called conservative is we're going to learn eventually about conservation of energy. And conservative forces, what you start with is what you end with, and you can go backwards and kind of get that energy back. You can't get the energy back from friction. Once it's gone, it's gone. Friction is one of those, it's useful at times, but it's always a battle. Friction is always a battle in engineering. You're always, like, you either try to take advantage of friction or you're trying to reduce friction, but friction is always kind of sapping away some of your energy, generally to useless heat. Think of your own car. The energy that is inside the fuel when you combust it, it's lost as heat, but also every single point of friction. One of the main rules in your car is to try to reduce that friction as much as possible, except for the tires. The tires actually want to increase the friction. Again, friction's a big deal. Friction, it's everywhere. You have to account for it. Okay, so we got these two different forces. Honestly, how does this play into problems? This is not something... So like the most question I could ask you was like those last two questions I just asked you. That's the extent of this. Okay? So right now this is just kind of an idea. As far as how I would quiz you on this, these two questions are kind of the ways that it would show up. Does the path matter, yes or no? Okay. Fantastic. So that's kind of that segment done. Power. You all have heard of power before. Horsepower. Horsepower is a measurement of power. It's that the word power in it for that reason. Power is how much energy you're using per second. Power is the amount of energy output or used, depending on your frame of reference, per second. How much energy you convert from one form to another per second. Your all's light bulb, and the unit for it is watts. So in SI units, it's watts. There is a direct conversion between horsepower and watts. Like 1 horsepower equals some number of watts. I don't know it off the top of my head, but you can look it up. A very common example of wattage is light bulbs. This is probably where you've actually seen this word before. If you buy a 50-watt light bulb, that's how much energy it uses every second. How much electrical energy it uses. And it doesn't destroy that energy, it converts it. So when we're talking about energy here, it's not how much energy it destroys, it's not how much energy it creates, it's how much energy it transfers. Hence the work part, dWdt. Work is how much energy you transfer. Oh, how much energy do I transfer per second? That's power. That's power. When someone has a lot of power, it doesn't necessarily mean that they output a lot of energy. What it means is they output some amount of energy very quickly. Now, that could be a lot of energy in a short period of time or something like that, but power is how much energy it can output really quickly. Alright, so we'll do some problems with this and it'll kind of make some more sense. A person lifting a 50 kilogram dumbbell, 2 people doing it, If they lift it, one lifts it fast, one lifts it slow, same work. The work done is exactly the same. The person that picks it up quicker, more power. So if you can lift that thing really quickly, more power, but the work is the same. dWdt, change in work over change in time. Change in energy transferred over time. Okay. So let's look through this problem. Coal is lifted out of a mine a vertical distance of 50 meters by an engine that supplies 500 watts to a conveyor belt. How many kilograms of coal per minute can be brought to the surface? Ignore the effects of friction. Very important to ignore the effects of friction. Notice in this problem, it does not tell you the path that this conveyor belt takes. This conveyor belt could be really steep or really not steep. Doesn't matter. Gravity is a conservative force. We don't care the path this takes as long as it's going up by 50 meters. So is it conveyor belt like this? Is it like this? Doesn't matter. Is it a really windy conveyor belt? Who cares? All we care, so I'm just going to do the simplest shape I can. Boom, there's my conveyor belt. Who cares what the angle is? Doesn't matter. The height that it goes up is 50 meters. Not really much more to show here. You know, there's a bunch of coal on it. Whatever. Let that coal go. Woo. All right. What's given, y'all? We have a vertical distance. We have our, I guess we could call it height. I don't know. Sure, I'll call it h. Doesn't really matter. We have a power of 500 watts. And we are trying to solve how many kilograms. We're trying to find mass per minute. We're trying to find the mass per, well, that's going to be a weird thing. Mass per second equals question mark. Okay. Well, okay, it says mass per minute. I'll put mass per minute, but we're going to end up doing it in seconds and then converting it. Mass per minute. Okay. So you may look at that. I'll let y'all think for a little bit. See if you can parse out some ideas. Spend 10, 20 seconds think through, what the heck do I do? How the heck do I go about this? Maybe you'll have some ideas, and we'll kind of flesh them out. What do we do? Yeah. For power?
In the slides that I downloaded, it just says that P equals W over T, but in yours it says W.
What did I have it as before? W over T?
W over T.
Yeah, this was just to make it more correct. dWdt. In general, most of your problems will just be W over T. This is a bit more accurate to be. There's a mosquito, I killed it. I saved you all. Thank you. Yeah, dW just, if that changes over time, if that work changes, we have to kind of do the derivative. So technically it's like delta W over delta T, but D, because that's a bit more accurate, like, yeah. Yeah, that's a good question. Okay. So what do we do here? Well, we think to ourselves, what is the definition of power? Power is, again, I'm going to put that, this is a good opportunity to kind of show what I was just saying, dW dt, which for a constant thing, the change in work over the change in time. That's for a more, if it's like a constant kind of flow, we can put that instead. Change in work over change in time. Okay, and then we say, what's work? Well, the amount of work done, the amount of work that you do is the integral of f dot dr. And you look at that and say gross integral. And you think to yourself, what forces are at play here? Oh, there's forces? Guess what we get to do? Free body diagram. Yay! Yay! So good. And in this problem, we have gravity, but we also have the conveyor belt, lifting it on up. So those are my forces. So I've got the conveyor belt lifting it on up. I've got gravity pulling it on down. All right, so let's make this onto a new slide. Oop. All right, so that means we got a constant force here. Gravity is going to be constant. That's going to be constant. So the total work done on this thing is going to be FA minus FG, which equals FA kind of minus mg. Okay. And then we're also going to remember, it doesn't necessarily say it here. It's not necessarily clear. We're going to assume a constant velocity. We're going to assume a constant velocity. Why are we going to assume a constant velocity? Because otherwise this thing would be speeding up infinitely. Like, if we assumed that it wasn't constant, that would mean my conveyor belt is getting faster and faster and faster and faster and faster and faster forever and ever and ever and ever and ever, and that doesn't really make sense. No one looks at a conveyor belt and says, wow, that thing's speeding up forever and getting infinitely fast and approaching the speed of light. No. So, we're going to assume a constant velocity. What does that do for us? What does that do for us? That says that FA minus FG equals 0. Fantastic. Why do we care? Because that says that FA equals mg. The force that this thing is pushing up on it is equal to mg, because the acceleration is 0. Equals ma, a equals 0. Okay, long story short, this thing's beating gravity. Okay? So we go back to this equation. Again, there's a lot of kind of concepts in this problem. It's a really good problem that kind of connects a bunch of ideas together. I like it. Great problem for y'all to kind of work through, think through, and you've got it kind of worked out. Well, you'll have it worked out. So this says that the delta work equals the integral of mg times whatever path it takes. Now, remember when we talked about gravity, we really only care about the up-down. Remember when we do this integral, I'm never going to make you all do left, right, stuff like that. So this dr becomes dy because the path doesn't matter, because it's gravity. Gravity, we just said the path doesn't matter. So if you integrate this, it's just mg times delta y, however high I went. That's the amount of work done. Now, fun fact, we just derived conservation of energy. Woo! Now technically, okay, there's a negative in front of this, but you know what, let's just call this h. Oh, did it do the thing? Ghost, are you here? Yes. Alright. Oh, it's going to be so sad I have to rewrite all this. Okay, please hold. Okay, so it's going to, yeah, it's gone. So fun. So, what does this tell us? It tells us that the force of lifting something is mgy. Spoiler alert, that's potential energy. We're going to learn about that next week. But, hey, you get to see where it comes from. How exciting. Again, this is kind of a worst case scenario. The math here isn't hard, but the concepts. We're using so many concepts together, which is why I think it's such a fun problem. Okay, so lightning quick. Got to rewrite all that stuff. So equals ma, a equals 0, fa equals mg. Therefore, delta w equals the integral of mg dy equals mgh. How high up we went? 0 to h. Technically, yeah, mgh. Okay. And then we put that in here. It's all coming together. Power equals the change in mgh over the change in time, the change, again, we're going to learn next week, this is potential energy, how much potential energy went up. The change in the energy. What kind of energy did I gain? This type, mg times h. Now, we look at this. Does my mass change per second? The amount of mass? Yeah, that's actually what it says to find. Does gravity change? No. Does the h change? H is h. It's how high up we go. So we get this equation. We pull out the g, we pull out the h, and we get delta m over delta t. The amount of mass I'm moving every second. Because this thing is constantly moving mass every second. And so you put in the numbers. So we have 500 watts equals 9.8 times 50 times the change in mass per second. We do the math. I give myself more room through the power of technology. This is a fantastic problem for you all to try to figure out on your own, because it uses so many concepts, so many small pieces. And if you can work through this one on your own without just like having the solutions open and just looking at it constantly, that means you're going to understand a lot of the individual pieces, and it'll be great, great, great practice. All right, so we get out of the calculator. I have to do the last step because even once you calculate this, we're not done. There's one last tiny step, and it's an easy one. You're going to be like, we're not done yet, but it was so much work. The amount of mass I move every second will be 1.02 kilograms per second. The problem isn't asking for the kilograms per second. It's asking kilograms per minute. I'll give you all 10 seconds, 20 seconds. How do I go from kilograms per second to kilograms per minute? Think in your head. See if you can figure out what conversion you're going to do. Pro tip, think what makes sense. Am I lifting more in a minute or less in a minute? That's how you should do these kind of unit conversions, is just thinking through what makes sense. If this is what I'm doing every second, am I doing more than that in a minute or less than that in a minute? That's how I do unit conversions. I don't do all the dimensional analysis stuff. That's too much brain power. If I want to go from kilograms per second to minute, I know it should be more. I should do more in a minute. I know there's 60 seconds in a minute. So I multiply by 60, the logic being, this is how many seconds per minute, and you get that this thing can lift 61.22 kilograms per minute. All right. Good problem. Lots of things. Lots of things. Obviously, I'm not going to ask something like this on a multiple choice. That'd be wild. But you know, maybe there's parts of this that would be like a fair response. Just because I love it. It uses so many concepts. Yeah?
So you have, there's one point where there's mg, dy, and integral. Why does mg just come out of the integral and change?
So in this case, that's a great question. I'm integrating over dy.
Oh.
And so my mass doesn't change with height in my g. That's a great question. Why does it come out, whereas later on, why didn't it come out? It matters what you're integrating with respect to. As time goes on, my mass is changing, but as I go up or down, the mass isn't. Yeah, great question. Love it. Yeah.
Why do you have to use it? Why don't you use like the 4 cents per times?
Yeah, I mean, to be honest, I keep using the integral because that's just the form I'm going to give you on the formula sheet. But the reality is, if you all have a constant force, it's just force times distance. If they're lined up with each other. The reality is, when your force is constant like this, you can just realize, I don't need to do an integral. It's just going to be FD cosine theta. F is the force, D is how far I moved, angle is the angle between them. That is a great point. That is a great point, yeah. But that requires you to understand this only, that FD cosine theta, only is true for constant forces and constant angles, which the reality is, you'll know it's not constant because I'll give you a function if it's not. So, yeah. Yeah. All right. Any other questions on this? There's a lot that went on here. I don't mind sitting here for a little bit. Okay, but again, please, 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 look through this one. I love it. I think it's really great. The only thing that I was like, I probably should have put in the problem, it's going up at a constant speed. That's one thing I probably should have clarified. But now you know. Okay. Next, this is cool. You get to calculate your electric bill. Now, this one's kind of technically a Physics 2 thing, but the ideas work. I will be straight up honest with you. I'm not going to make you calculate power bills on the test, but it's worth spending a few seconds and doing it real quick. So if you all are paying electricity, you are charged kilowatt hours. Kilowatt hours are literally, wattage is the energy per second. Multiply that by time and you have energy. Kilowatt hours is just energy per time times time. If you multiply energy times, so kilowatt is just 1,000 watts. So kilowatt hour is literally just saying 1,000 watts, which is 1,000 joules per second. You know what? Let's just say 1,000. Kilowatts is energy per time. If I multiply that by hours, which is time, boom, you get energy. This is what you're getting charged for. How much energy does your house use? And this is one way they show it. Again, I'm not going to test you on this, but we'll quickly do a problem on it. How do you actually calculate this? Say you have a 50-watt light bulb. You take that 50-watt light bulb, you convert it to kilowatts. How many watts are in a kilowatt? You divide that by 1,000. So for example, 50 watts is 0.05 kilowatts. Okay? You multiply it by how many hours it's used. That's where the kilowatt hours comes from. And on your power bill, it depends state to state, county to county. Every single state, every single county charges a different amount per kilowatt hour. Why is it different? That's incredibly complex. Depends upon the energy generation in that state. Where does it get its energy? How does it get its energy? You know, as time goes on, energy will probably be cheaper during the daytime and more expensive at nighttime. In Florida, as solar power becomes more usable, it's cheaper to produce during the day. At nighttime, it's produced otherwise. So kilowatt hours depends on where you're at, but it's on your power bill. You can literally see it's like 7 cents per kilowatt hour, something like that. Okay? So let's do a quick calculation with this. Pretend you have a powerful 1,500 watt microwave. My microwave at home I think is like 700 watts, but they go up or down. It's literally how much power, how much energy can your microwave output per second. And you use it for 3 hours during the month. If your electric company charges 10 cents per kilowatt hour, how much did your microwave cost you that month? Again, it's a cool kind of calculation. It takes that idea of power and actually connects it to something that you all experience every single day. So remember the steps. Convert watts to kilowatts. Convert watts to kilowatts. Multiply it by the hours. So it's basically kilowatts, however many that is, times hours, times dollars per hour, per kilowatt hour. That's the, so this one you can kind of ish do in your head. But you can also use a calculator. And this is real numbers. Like if you have a 1,500 kilowatt microwave, which is a possibility, it's a little high, but it's a possibility, and you use it for 3 hours, and your electric company charges 10 cents, this is literally what it costs you every month. Which is cool. Like these are all real numbers. I'm just Googling the cost. So Florida, average cost per kilowatt hour right now, it depends where you look. It says actually like it's like 12 cents, 15 cents. It really depends. You can check your electric bill and find out for yourself. All right, we'll close this at 45. So 5, 4, 3, 2, 1. So if you did the conversion, you got 1.5 kilowatts times 3 times 0.1 comes out to 0.45. That's the cost of a microwave. It's not very much. Not very much. Makes sense. You don't run it very much. So then the question is, which devices cost you the most? The ones that run the most hours and the ones that have the most wattage. That is your air conditioner and your refrigerator. You can literally look on those devices somewhere. It should tell you the wattage, or you can Google it, and you can do the math and figure out how much it's costing you each month for that electrical device. Woo, fun things. This also is a cool exercise to show you why LED bulbs can save you a lot of money. If you imagine how long a light bulb is on in your house, multiply that by how many light bulbs you have, and just determine, hey, what's the wattage difference between an incandescent light bulb and a LED one? You can save yourself actually like a significant amount, like $50 or something, just by changing all your light bulbs to LED. On the map. Cool. All right. So there you go. That's power. Power is just how much energy used per second. Kinetic energy and work energy theorem. Really simple. It's going to be a really simple theorem. At this point, like the rest of this, will go much smoother. We've kind of spent done the concepts are the hard things here. The next concepts aren't too bad. Take a guess. How do you gain kinetic energy? This is something you probably learned in middle school. Most of my high schoolers kind of have heard this term, so I'm trusting that between then and now you all haven't forgotten it. Maybe you have. How do you gain kinetic energy? Is it by going faster, going higher, charging it up, or absorbing heat? If you don't know it, that's okay. I'm going to teach you, but I want to just show that most of you all do know this. Most of you have heard the word kinetic energy in middle school, high school, somewhere. TV, I don't know. All right, we're going to go to 40 seconds. And 5, 4, 3, 2, 1, boom. Kinetic means movement. The faster you're moving. Nope, not higher. Faster. Great job. And again, if you didn't know that, that's okay. That's okay. My feelings aren't hurt. All right. Kinetic energy is associated with an object's relative motion. We'll get to a slide on what it is exactly. Okay. So this is a written out derivation of the theorem. I'm going to go ahead and actually solve this in front of you all because I think it's a little bit, I say that. I'm going to actually just walk through this. I'm not going to spend the time doing it myself. I'll walk through each of the steps. You don't need to know this, but something really important in physics and engineering is to see that we didn't just make it up. So, we start here. We're cool with that, hopefully. That's what we've, like I gave that to you all at the beginning. Alright, we say force is M times A. That's Newton's second law. Hopefully also feeling okay. That's something we've talked about as well. Well, then we remember that, the definition of A. Look at all these things we're getting to use. A is literally defined as the derivative of B with respect to T. 1D kinematics, talked about that. So we're just substituting a bunch of things that you've learned before. And then we do a math trick. We just straight up say I'm going to multiply by 1. But by 1, I mean dx over dx. That's just multiplying by 1. You can do that. You're allowed to multiply by 1. It changes nothing. Dx over dx equals 1. All right. Now, what does that do for us? We rearrange the terms inside the integral. We're going to do some weird math things that seem weird. Derivatives, in math class, they don't like this, but we do this all the time in physics. We rearrange the terms. So this is where we started, and we just move those x's around. We swap places. We swap those two things. dv and dx swap places. So now it's dx dt, and now it's dv dx. Again, you don't need to know this, but it's just kind of cool to see where this comes from. Okay. What happens then? These dx's cancel. Okay, so what? Oh, look, we're left with this. Oh, what's dx dt? Oh, that's v. So it's just a bunch of logical steps. Each step is not a big deal, but when you put them all together, we end up with this result. And I will give, let's see, I think that's literally the next slide. I'm going to have you all integrate that. You can do that. M times v with respect to dv. Do it to it. What is the integral of mv dv? we are going to say that mass does not depend upon velocity. We're going to say that the mass does not depend upon the velocity. I can't think of any object that is the case. Well, okay. Rockets, I guess, weirdly. They lose rocket fuel and their mass changes. And mass is a constant. Mass is a constant. That's what I'm trying to convey to y'all. Give y'all a minute 30 for this one. I want you to do the integral. It's good practice. And I'll be straight up honest with y'all. The reason I had all those steps typed out, I can almost guarantee you I would have forgotten one or two of those steps if I did it in front of y'all. It was a bunch of steps. There's like 7 steps in there. But it's cool. Each step is a small thing. And I don't need you all to be able to do that derivation. But it's just kind of cool. Alright, 20 more seconds. See if y'all can do this. Let's see how we're doing. I can see the responses. Yeah, look at y'all. Alright, 5, 4, 5, oh sorry, I said 130. 5, 4, 3, 2, 1. Yeah, there we go. We're past the 130 mark. Alright, so this one, the integral should be fairly straightforward. We pull out the m, so it's just v dv. The integral of that is mv squared over 2 from va to vb. Which equals, if we just rearrange this, 1/2 dividing by 2 is the same as 1/2. MVA squared, nope, wrong one. MVB squared minus 1/2 MVA squared. Look at that, y'all just derived kinetic energy. This is something that you all may not have learned before. So in your middle school and high school class, you may have seen that kinetic energy was 1/2 MV squared. It didn't just come out of nowhere. It came out of an integral. The beauty of calculus lets us find these things. The more skills you have, the more you can discover things. The more math is a tool. The better you get at speaking the language of math, the more you can discover. The more you can kind of do. It's the same way, math is a language. As weird as that sounds, math is a language of logic, cause and effect. 2 plus 2 is literally a math expression. It's a language. It says if I have 2 things and 2 things and I add them together, I get 4 things. The more of this language you understand, the cooler stuff you can do with it. Just like the more English you understand, the cooler things you can do with the language, the more you can express, the more ideas. Philosophy and all that relies on a good understanding of the English language. Lawyers literally are just very good at speaking English in a very precise, technical way. You all, engineering majors, computer science, you're going to be very good at speaking math. Yeah.
Would it be a good idea to memorize that?
The derivation, you 1/2 MV squared, that'll be given on the formula sheet. Yeah, so this equation, kinetic energy is 1/2 MV squared, that you need to know. The derivation, no. You don't need to know the derivation. But you do need to know that, I say no, this is also given on the formula sheet. I will actually post the formula sheet by probably this next week for the next test. I've been working on your all second test already. And so I made the formula sheet updated. Yeah, so kinetic energy is the energy associated with the moving object. The variable for it is K. Sometimes you'll see KE. Both mean kinetic energy. It's joules. Energy is joules. 1/2 MV squared. And unfortunately, we probably don't have time for the next question, but that's all right. We don't have that much. We'll probably finish this stuff Friday, no problem. I say probably, we will. Maybe you can start the next stuff early, who knows. But there you go, kinetic energy. The equation you probably seen this before. We got to see where it came from today. It's cool. I love it. All right, y'all, if you got any questions, comments, concerns, let me know. Don't forget about that extra credit survey thing. If you need feedback about the test, it's good for me. It's good for me. It's good for you to get those points. And you all have a great day. See you all Friday.